In the previous videos, we looked at some examples of applying the Bayes theorem for decision making. In particular, we looked at one example of using Bayes theorem to understand the results of medical tests. And then in another example, we looked at how to use Bayes theorem to understand the results of the lie detector, right? Based upon polygraph. So the basic results of the Bayes theorem is that the posterior distribution for a specific model, say y, conditional on a given set of observations or data equals to this conditional probability of the data conditional on a specific model y times the prior of the model, and then divided by the marginal for the observation or the data. Right, and this is actually a continuous form of the Bayes theorem, and then this is a discrete form of the Bayes theorem. One of the things that we have to understand in the context of machine learning is that in the examples that we have looked at, both for the medical tests and also for lie detector, those conditional probabilities and the priors, the values for the conditional probabilities and the priors were given to us. So we have those values. Then all we have to do is to actually stick those numbers into the formula, and then we can actually compute the posterior. And the posterior is going to be the basis for decision making. Do we trust the results? Do we do more tests? Right? Those kind of decision making are based upon this posterior probability based upon a given set of observations, and we're using this formula explicitly, right, by sticking those given probabilities, given values for the probabilities into the formula. But in realistic machine learning problems, those values were not given. Those values have to be learned. Those values have to be learned from training data. Training data means that it's a past data, right? Past data, and we have to use those past data to actually come up with reasonable values for those different conditions, different probabilities. I mean, right? So by now let's try to understand. Let's try to understand those Bayes theorem, those equations from the Bayes theorem, and then how we can actually use those for machine learning. Here it's just a copy of the continuous form of the Bayes theorem and then this discrete form of the Bayes theorem. And one of the things that we need to understand is that in practice, usually you don't have to actually compute the denominator. Right? In the examples that we have looked at, the denominator were explicitly computed by using this specific summation. Right, this specific summation. It's the prior for a specific model times the condition of the data, the conditional probability of the data given that model, and then do a summation over all the different models. Right. So here we are using y to represent the model and using x to represent the different observations or data. Right. And the denominator will actually compute it in this using this particular equation. In our two previous examples, right? But in practice, you usually don't have to compute the denominator. Why? Why is that, right? Because we're not exactly computing the exact values of the posterior. Instead, we're actually comparing the posterior for different choices of the model or y values, right? And then the denominator is purely just a function of the data x. It does not depend upon the model y, right? So for a given set of data, the probability of the posterior probability of different models of y, different values of y, is going to be independent. The relative values for different posterior probability of different y is not going to depend upon the denominator. Right. The denominator is going to be the same for different values of y, but a given set of values for x. Right. So the denominator can be neglected. Right. So in practice, we don't really have to actually compute the denominator because we're comparing the posterior for different values of y for the same values of x, right? So in practice, the actual formula, the actual equation that we are going to use is not exactly equal to, but proportional to, right? So this symbol actually represents proportional to. So all we have to do is to actually compute a representation of the numerator, right? The denominator is going to be the same for different values of y, but the same values of x, right? And at this point, we need to introduce some terminology, right? In the literature of machine learning, you are going to see these kinds of names. One is called generative, the other one is called discriminative. You have two different approaches of using those equations. One is called generative, the other one is called discriminative, right? So what does it mean? What does it mean, right? Usually, for the generative approach, it means that you try to actually come up with some estimate of the posterior distribution by using the Bayes theorem. So you have to actually construct this conditional probability and then the prior, right? I was saying that you don't have to actually compute the denominator later on. Once we start to look at some examples, you'll understand why we don't have to compute the denominator, right? But for the generative approach, you explicitly construct the posterior by using this conditional probability, which we call likelihood. I'll explain what's actually the difference between the conditional probability and the likelihood, and multiplying it with the prior, right? That's called the generative approach. You are using the Bayes theorem explicitly by trying to actually estimate the conditional probability and the prior, right? So suppose you are doing a classification problem, right? Suppose you have two classes. This is x1, this is x2. You are trying to suppose this horizontal axis is x, right? X is some feature, right? Suppose we're trying to classify a set of rock samples into sandstone and shale, right? And then the horizontal axis is the porosity of those rock samples, right? And then you are trying to actually classify the rock samples into sandstone or shale based upon its porosity values. So you're trying to actually construct those posterior distributions for sandstone and shale using a set of training data, right? So suppose you are constructing those. So horizontal axis is going to be porosity, and then vertical axis is going to be the posterior probability, right? So suppose high porosity values often corresponds to, say, sandstone, right? And then low porosity values usually correspond to shale, right? And then you try to actually explicitly construct those posterior from some estimations of the conditional probabilities and the prior, right? If you try to construct those posterior distributions, right? Suppose you have constructed those posterior distributions, then once you are given a new test rock sample and then you got the porosity for that new test rock sample, right? You can compare the posterior probabilities, right? So suppose the test rock sample, the porosity for the new rock sample have a porosity that has a value that's about here, right? And then you just compute the posterior probabilities for the sandstone, right? And then the posterior probability for the shale, right? And then you're gonna see that the posterior probability for the sandstone is higher than the posterior probability for the shale for the porosity value of this new test sample. Then you're gonna say that this new test sample is gonna be a sandstone instead of a shale, right? That's called a generative approach. But there is a different approach, right? This kind of different approach is based upon directly estimating some aspects of the posterior, right? You're not exactly trying to actually construct the entire distribution, but you are trying to estimate some aspects of it, right? So again, for this kind of classification problem, what's that aspect that you try to estimate, right? If you actually look at the intersection of these two posterior probability, it actually corresponds to a specific porosity value, which is this particular point, right? So on the right side of this particular point of this intersection porosity value, the posterior for the sandstone is going to be higher than the posterior of the shale, right? And then on the right side of this porosity, then it's the opposite, right? So this value, if you can learn this specific value, this intersection porosity value, right, from the training data set, then you don't exactly have to actually explicitly construct the posterior values or compute the posterior values for new test data, right? All you have to do is to look at the porosity of the new test data, see if it's larger than or smaller than this critical interface porosity value, right? If it's larger than this critical value, then it's a sandstone. If it's smaller than the critical value, then it's a shale, right? So that's called a discriminative approach, right? And this kind of discriminative approach is based upon learning a specific criteria, right? That's gonna allow us to separate the different classes, right? And this is the classification problem, right? For regression problems, right? For regression problems, what we are learning is not actually the location of the intersections of the probability, right? If we are doing a regression problem, usually what we are learning is actually the location of the peaks, the location of the peak of the posterior, right? For classifications, we are learning the location of the intersections of the posterior, right? So later on, once we look at some examples, we will be able to actually tell the differences, right? And then a third point about how to use those equations is in terms of parametric or non-parametric approaches. So what exactly is a parametric approach, right? So here you have to use some form of the probabilities, right? If you assume a certain specific form of the probabilities, for example, if you assume the probability is a Gaussian, right? The conditional probability is a Gaussian. Then a Gaussian is parameterized by just two parameters, right? One is the average, the other one is the standard deviation or the covariance, right? In that case, you are calling your estimation to be a parametric estimation, right? Of course, you don't have to use a Gaussian, right? There are plenty of other choices for distributions, right? If you assume other kinds of distributions, then it's going to be different kinds of parameters that's going to be built into those mathematical representations of the distributions, right? But in any case, all those parameters will have to be adjusted based upon the training data, the given training data, right? And you adjust those parameters, you adjust those built-in parameters of those distributions through some kind of optimization approach, right? But the specific form of those distribution is actually fixed, right? But what about the non-parametric approach, right? Non-parametric approach is that you do not assume a specific form of the distribution. For example, you try to actually construct the distribution by using histograms. You try to estimate a certain form of the distribution by using histograms, right? Of course, histograms are dependent upon the width of the bins, right? There are better approaches for you to actually estimate the distribution using non-parametric methods, right? For example, you could use some form of the kernel, right? Kernel Gaussian, for example, you assume some kind of a kernel that's with a Gaussian form, and then the different Gaussians are located at the locations of different training data, and then you try to adjust the width of it and to give you a smooth estimation of the distribution, right? But those are called non-parametric approach, right? Histogram is one example, right? Kernel is another example, right? If we have time, we'll discuss them. But we're going to start with parametric form, with a Gaussian distribution, right? We're gonna start with this kind of simplest example. And then a fourth note is about the specific criteria that we use to pick the most likely model, right? In the two previous examples, what we have seen is that we picked the model that gives us the largest posterior probability, right? And this kind of criteria is called a maximum A-Posteriori rule, or MAP rule. And this kind of MAP rule is used quite often. It's used actually very often. It's probably the most widely used rule for picking the most likely model, right? The most but it's not, the MAP rule is not the only rule, right? And if you look into the literature, you're going to see some other rules. Some other rules are based upon the so-called minimum misclassification rule, right? You're not actually trying to actually pick the probability with the highest peak, but you're trying to actually minimize the area of the misclassification, right? So for this red distribution, everything that falls on this side of the critical porosity is going to be misclassified, right? If you just have this particular one distribution, right? It's supposed to be sandstone. It's supposed to be shear, but if you are using only this distribution to classify, then you're going to end up with a sandstone, right? So you try to actually minimize the area of misclassification, right? That's another kind of a rule, right? And under certain conditions, this MAP rule and this kind of minimum misclassification rule are kind of equivalent, right? But we are not going to sort of get into that. And then sometimes you have even more complicated rules. That's like a Bayes decision rule, right? But for now, we won't get into that. It's even more complicated, right? So we're going to start with MAP rule. We're going to do some classification examples based upon this MAP rule, right? The reason that MAP rule is used very often is because this MAP rule becomes this widely used maximum likelihood estimation, or MLE rule, given that the prior is uniform, right? So if you have a uniform prior, which means that this HY has exactly the same value for different values of Y, right? That's a uniform distribution. So for different model, for different Y values, if HY, this prior, is exactly the same, then the posterior is going to be proportional to only this conditional probability, right? Right? Because this one is a constant with respect to Y, right? And in this case, the MAP rule becomes the MLE, maximum likelihood estimates, right? And what exactly is this particular function, right? What exactly is this particular function, right? We're calling it the conditional probability given Y, right? For the conditional probability of X given Y, given the model Y, right? But what exactly is the distinction between the conditional probability and the likelihood, right? In some of the previous derivations, we actually looked at we were saying that the conditional probability is a probability of X, right? But it's not a probability with respect to Y, right? Why is that, right? Because the integral over X is going to be exactly 1, right? But the integral over Y is not necessarily 1, and usually it's not 1, right? So depending upon what exactly is given and what exactly is the function, what exactly is the independent variable, so you have different interpretations of exactly the same function, right? So when we call this function a conditional probability, we are implying that the model Y is given, right? We are actually treating this function as a function of X, the data, for a given Y, right? And then that's a conditional probability. So if the Y is given, if the model is given, and then we are actually estimating the probabilities for different X values or observation values, right? Then we are in what kind of a mode, right? We're actually in a prediction mode. We're actually making predictions about observations or the probabilities of different observations based upon a given model, right? That's exactly the definition of a prediction, right? We're making predictions. So if we are actually making predictions, then we are treating this function as a function of X, and the model is given. right? But we can also use this function as a function of y for a given set of x, right? So in that case, x is given, right? But we are trying to actually pick a model which actually makes this function makes the value of the function maximum, right? And if the data is given, and we are trying to actually pick a optimal model based upon the given set of data, and this is actually the training process, right? We're actually training the model. We are actually trying to pick the optimal model based upon a given set of data, and that's exactly the definition of the training. And then during the training stage, we're calling this particular function a likelihood because x is given. For the training process, all the training data are given. Right? It's from previous existing data, right? And then we're trying to come up with a best model based upon those existing training data, right? And in that case, it's a function of y, right? And this function of y is not a probability because its integral is not necessarily a 1, right? And usually it's not 1, right? The confusing part of this particular distinction of probability, conditional probability, and likelihood is that they are actually pointing to exactly the same function values, right? But we are treating the independent variables differently for different stages of machine learning, right? In the training stage, we call the x is given, so y is unknown. We try to actually get the best estimate of y. And in that stage, we are calling this function a likelihood, right? And then during the prediction stage, if you are trying to make a prediction based upon a given y, then that's a conditional probability of x, right? One example that I used in the class was about dice, was about a thought experiments, about a thought experiment using a dice, right? Suppose you walk into a bar. Suppose you walk into a bar, and the bartender shows you a dice, and he's asking you what's going to be the probability for the next throw to show 6 points upward, right? You say it's 1/6 because it has 6 sides, right? And if the dice is fair, then the chance of getting 6 points is going to be 1/6, right? So the bartender throws the dice. It's indeed 6 points, right? You get 6 points, right? And then the bartender asks you again, what's going to be the probability for the next throw to give you 6 points? You think that because the different throw of the dice is kind of an independent experiments, right? So you think that it's still 1/6. It's still 1/6, right? So the bartender throws the dice again, and then you get a 6 point again, right? And then he asks you again, what's going to be the probability for you to get 6 points for the next throw, right? He repeated this process for like 10 times. He repeated this process 10 times, right? And for every throw, you are getting 6 points. You are getting 6 points 10 times in a row. And then for the 11th time, he asks you what's going to be the probability for the next throw to get 6 points, right? What do you answer? How do you answer the question, right? Is it going to be still 1/6, or is it going to be a different number, right? So if you are treating this particular function as conditional probability, and you assume that the dice is fair, so the dice is fair, right? Dice is fair, so y is given, right? What's going to be the conditional probability of getting 6 points 10 times in a row, right? That's 1/6 to the 10th power. It's a very, very small number, right? That's the conditional probability for getting 6 points 10 times in a row, right? Given this assumption, your model, right, this dice is fair, right? It's a very, very small number, right? But for the 11th throw, how do you answer the question of what's gonna be the probability for the next throw to give you 6 points, right? So don't forget 1/6 is conditional probability. 1/6 is based upon this assumption that this dice is fair, right? But if you got 6 points 10 times in a row, then the likelihood of the dice is fair is going to be extremely small. It's exactly the same number. It's 1/6 to the 10th power. It's a very, very small number, right? So the likelihood that the dice is fair is going to be extremely small. So you should question if this model is actually correct, right? In fact, the model that the dice is fair is very unlikely to be correct, right? So you should actually adjust your model now, right? Given the 10 throws that you have watched in the past, the 10 existing throws, right? 10 existing training data, right? The most likely model is going to be that the dice is not going to be fair, right? It's unfair dice. It's a loaded dice, right? If you accept that, if you adjust your model to be the assumption that the dice is unfair, it's a loaded dice, then you should guess that the next throw is still going to be 6 points. The 11th throw is still going to be 6 points, right? It's not 1/6 anymore. It's going to be the chance for you to actually get 6 points for the 11th throw is still going to be it's going to be much higher if the dice is loaded, right? It's not 1/6 anymore, right? So let's think about this kind of a thought experiment, right? And then once you understand how this kind of a function, how this same function is being interpreted in different ways during the prediction and training stage, it's gonna be a lot easier for you to understand the distinctions between conditional probabilities and the likelihood.